Good morning. In this lecture series, we see about the one-dimensional problem on the topic of Bar Element Stiffness Matrix. One of the one-dimensional problem we always consider as a Bar element. So how to calculate the stiffness matrix for the Bar element? So let's see on the topic now. So let's suppose the Bar element stiffness matrix or direct method. So it is a fundamental approach to understanding the finite element analysis through the equilibrium principle. So understanding the bar element like a geometry, properties and assumptions. So for considering geometry, the bar element are one-dimensional members connecting the two nodes with the length of L. They resist only the axial force along their centroidal axis. So the material properties defined by the elastic module like a stress-strain relationship and a cross-sectional area which together determine the axial rigidity. So what are the key consumptions are the linear elastic behavior, small deformation theory, uniform cross-section throughout the length, and axial load only, no bending or shearing. So these are the empathize the when understanding the what are the bar element, if you're considering the what are the property we have to assumption for that. The next one is local coordinate system and the element degree of freedom. So as per the local coordinates, okay, each bar element has its own local coordinate system aligned with the element's axis. So degree of freedoms are there are two dots bar element as the 4-degree freedom axial displacement like a U1 and U2 for the respective of node 1, 2. If you have a node 2 and 3 means U2 and U3. So likewise, the corresponding force R2 you have to represent like F1 and F2. So the sign conventions are the positive displacement and force act as a positive x direction. The tensile force and the elongations are the positive and the compressive force are the negative. So what is the deriving the element of stiffness matrix using the direct equilibrium? The direct method applies the fundamental equilibrium and the compatibility the principle of two extents establish the force displacement relationship. As we have to apply the unit displacement, impose the unit displacement at node 1 while the restrain the node 2, the calculating the resulting force using the stress strain relationship. The equilibrium equations for axial deformation, the internal force, we have to calculate that AE by L, that is the L, change in length. Okay, so here the apply the equilibrium at the each node, establishing the force balance. The superposition, the repeat for the unit displacement at node 2, then the superpose the resulting to obtain the complete stiffness matrix for relating the all the force for the displacement. So the finally matrix formation, as we know that it is called as a general matrix, is F is equal to K into U. So here K is always is like a square matrix, that is equal number of rows and column will be there for maintaining the axial rigidity terms. So what are the transformation for the local to global coordination systems? So as a real structure, the compares the element to orient the various angle and the transformation matrices convert the element property from the local to global coordinates. So the rotating angles and the transformation matrix and the global stiffness, the rotating angles, they measure from the global x-axis, the local element axis, defining the element orientation in the space. So the transformation matrix, the constraint the geometrical methods terms is like a trigonometry method systems cos theta and sin theta that related with local and global displacements. So global displacements is nothing but K is equal to T transport and K into T, expanding the 2 by 2 local matrix into the 4 by 4 global matrix. So as the final conclusion of this bar elements, we have to categorize the fundamental assumptions and the key property, derivations of the foundation, matrix characteristics, and application analysis. For the fundamental assumptions are the uniform cross-sectional area, linear elastic material, axial deformation only, the stress element behavior. So derivation foundations are Hooke's law, displacement field, shaping function, and applications and analysis are the stress structural assembly, axial stress predictions, elongation calculation, overall structural responsible. So these are the summaries of the that is a bar element of stiffness matrix. Thank you.